Hi, in this session, we are going to discuss about neural network and its implementation from the scratch. First, we will see what is a biological neuron. A biological neuron consists of four important parts: dendrite, soma, axon. Dendrite, soma, axon, synapse. Dendrite will receive information from the environment, and soma process that received information, and axon will produce the output, and the synapse will act as an interconnect between the more than one neurons. Uh, brain consists of trillions of neurons. In that neuron, all the neurons are collecting the information from the environment, so it will be interconnected together to process all the signal. That time the synapse will act as a interconnect between the neurons. The received signal may be excitatory signal or else incipitory signals. Excitatory signals means it make the neurons to fire, and incipitory signals mean it will not make the neurons to fire. Actually, while talking about the inputs, we must talk about the weights. Actually, from the working of biological neuron, the artificial neurons are created. So, how the biological neurons parts are compared with the artificial neurons? See this table. In the biological neuron, dendrites is equal to the input in the artificial neuron, as soma in BN is equal to the node in the artificial neuron, and axon in the biological neuron is equal to the output in the artificial neuron, and synapse in the biological neuron is equal to the interconnection in the artificial neuron. A single node in the artificial neural network is called a perceptron. We call it as a perceptron. This is a simple perceptron. It consists of only input layer, and we have some kind of input. That inputs are summed together. That inputs are summed here, and that will pass to that summed output is passed to the activation function. Then we will get the output. Here we see the term weight. Here each input we assign some kind of weights. This is input 1, input this is input 1, this is input 2, and sorry, input 2, input 3, input 4. See why we have to assign a weight. To give a priority to the input, we will assign a weight to the inputs. See, suppose the two persons is coming to you, they are giving some kind of information to you. You process that information, and we will give for whom we will give a priority. Based on that only we react to the particular person information. The same thing implemented here. If you are giving a more than input in the input layer, we must assign a weight to the input. But the machine don't know how we will give a priority to the input. It randomly assign the weight to the input, and during the training, it will assign the weight randomly. Then during the back propagation, it adjusts the weight. So in the perceptron, these are the parts: input layer, weight, bias, activation function, and output layer. I already explained the term weight, and what is bias here. So the bias is nothing but it is a error term. Actually, to make our model to fit with the real-time data, we can include a term called bias. For example, if a teacher give a mark to the particular student at a high, only boys he or she give a very good mark, we say that the faculty is biased to boy student only, or else the faculty is biased to particular students only. But that will not happen in the real network. To make our model to the all kind of data, all kind of real time data, to best bit of our data, we introduce a term called bias. So actually, the weight and bias is related with the linear equations called y equal to mx plus c. Here, in this, here y is called the output, and m is called the weight. The m related weight, and x is called the input, and c is called the bias. We are compare that. neural network model with the linear line equation y equal to mx plus c. See here, if you are having an equation y equal to mx without a bias, it always pass through the origin. It is not fitted with a real-time scenario. Every time not a equation always pass with the origin. The lines are may pass with different direction. That's why the bias will decide that. To make our model to the fit with the real-time data, we introduce a term called bias. From this diagrammatical information, diagrammatical representation, you know the importance of the bias. See, if you are changing the weight, well, I already informed that initially I said that we randomly assign the value. Suppose the weight value 1 is changing from 1 to 4 and weight 2 value is changing from 0.125. What will happen to the curve when you are plotting that curve? It will blue color shows that value weight one value is 1 and weight 2 value is minus 0.5. So depending upon the chosen weight value, that inclination of that curve, the steepness of the curve is varied. And also if you are changing the bias value, the again the bias also changing the um, curve in the plotted area. Next, it is an example perceptron with two inputs, and we assign the input 1 is 0.8, input 2 is 1.2. We randomly assign weight to the two input and also introduce a term called bias. So to find the summed input, this is a formula. Output equal to sum into weight of input into weight plus bias. Formally, that is mathematically we can represent summation of xi wi. Here we are using the activation function as maximum of 0 comma z. The activation function will decide the output. It is equal to axon. See here, we find the summation of the input weight 1 into input 1 and weight 2 into input 2 plus bias value. So plus bias value, this is a bias value. We randomly assign the bias value is 0.5. If you are doing the mathematical calculation, we will get a 2.2. So for activation function, see that is activation function is maximum of 0 comma z. Okay. So here, if it is 0, if the combination, that is C, it is called a combination. That's why they mentioned that combination. If combination is less than 0, we take that activation output as 0. But in our problem, we get a combination value is 2.2. It's greater than 0. That's why we take the combination value as a activation function output. Actually, many kind of activation functions were there, but I have discussed only two important activation function whichever will be used for binary classification and multi-class classification. A sigmoid function is used for binary classification and software function is used for multi-class classification. We will see the formula of both sigmoid and softmax. Sigmoid mathematical equation is 1 by 1 plus e power minus x. This is the summed this x representative. We calculated the combination of that combination is included here. Then for softmax, e power zi divided by summation of e power zi. It means say equal to 1 to k means it is mentioned the number of input samples involved in that particular calculation. If your k number of calculations were included, for example, if I am having 3 number of calculation, I will sum to the 3 numbers. If we see the example, people will have idea about how the software function will calculate the output. See here in output layer, I have 1, 2, 3, 4, 5 values. So first one is e power 1.3. For this zi, I substitute 1.3. I substitute 1.3. Then this summation of all things e power 1.3, e power this 1.3 plus e power 5.1 plus e power 2.2 plus e power 0.7 plus e power 1.3. All these are summed under here, and the numerator is e power 1.3. This is the first term. So this first term is e power 1.3 divided by the summation of all the terms e power. The second term belongs to e power 5.1 divided by summation of all the terms. This is belongs to e power 2.2. See here, if you are having in our output, this is belongs to class 0, this is belongs to 1, this is belongs to 2, this is belongs to 3, this is belongs to 4. Okay, so see the class 1 probability, it is 0.90. That's why we conclude that our given input is belongs to class 1. This is what softmax function will work. This is an example of single layer feed forward network, and this is an example for multi-layer feed forward network. Here we introduce a term called hidden layer. Actually, in a perceptron, there is no hidden layer. It has only input and output. There is no hidden layer. In a multi-layer perceptron, there is a introducing hidden layers. We will see the simple classification problem using a perceptron. Here we are having two sets of data, that is a set A equal to ABC and B equal to PQR. We plot that data, that is A belongs to ABC. That's why marked as a empty circle, and PQR is marked as a dark circle. How we will do, the perceptron will do a classification using a normal perceptron learning algorithm. We assumed that y output equal to 1 means that belongs to class A. Y out equal to 0 means it belongs to class B. This is a sample network for this given input. Actually, we are having three inputs. 1, 2, 3. We are having through three inputs. That is, this class should take the input pattern of the form x1, x2. It take the form. Actually, this is, sorry, this is belongs to x1, this 3 belongs to x2. So that's why this x0 belongs to bias. So x1, x2 bias value, for that bias we assign the weight value is 1. So bias value is 1, for that weight value is -1. For input 1, assign the weight value randomly, we choose, and the weight value is -1/3. For this one, 1. So all this is the sample perceptron structure for the given classification problem. See here, we already know the input, how we calculate the summation of the input. This is the mathematical formula for calculating the summation of the input. So yin equal to, so -1 into 1 first. This is the first term in the summation. Second one is -1/3 into x1 value and +1 into x2 value. Okay, so when you are simplifying this equation, we will get the equation is x2 equal to x1 divided by 3 plus 1. So if you are considering the input pattern, for example, if you are having 6 samples in the input A, B, C, B, Q, R, what is the x1 value and x2 value? From the given data, we will write, from the given data, we write the x1, x2 value, and we will calculate the, using this equation, we will calculate the net input value. And we will calculate the activation class of the particular input. Okay, if the output already we defined that if the y out is equal to 1, that belongs to class A, and y out equal to 0, that is belongs to class B. Already we defined that. Okay. We understood that this equation represents the straight line will divide the data set into two parts, class A and class B, that is class 0 and class 1. Okay. Next, consider a XR truth table. If you are plotting the XR truth table as a plot, so we can't able to, using a single line, we can't able to divide into two classes. So to rectify this non-linear, actually the perceptron is only suitable for linearly separable data. So this is XR is non-linearly separable data. That's why we are not using the perceptron model to solve the, to design a XR gate. For that, to rectify that problem, we are moving for a multi-layer perceptron. So in a perceptron, we will calculate the error using the, what is the error here? If you are, there is a difference between predicted output and actual output. That error will be calculated using mean square error. This is the formula for mean square error. This n means that number of samples in the input, and y it is a actual output. It is a actual output. Y cap is a predicted. Sorry, y cap is the predicted output. We see the difference between actual output and predicted output. Why this square? To avoid the negative terms, we include the square. Next, we will implement a simple neural network using from the scratch. We will implement. For example, if you are taking the OR gate, we know the OR gate truth table. This is a symbol OR gate, digital symbol of the OR gate. If you draw the truth table for the OR gate, this is a truth table. We consider this the input 1, input 2, and output. See, it is a perceptron for OR gate. A node is there, 2 input and 1 bias value and output. See, we will assign the weight value randomly. Here we will take input 0, 1. See, for 0, 1, the output, actual output is 1. We are going to find the predicted output value. Okay, we assign the weight randomly and we will calculate the summation. We know that weight into input, and bias into bias value into. Some people will assign a weight to the bias value also. It's our wish. Okay, this is a summation value 0.8. This will apply to the activation function. We already know this is a sigmoid activation function. Why we took sigmoid activation function? It is a binary classification problem. How it is a binary classification problem? See the input data. This data consists of the class 0 and class 1 here. Okay. Here we are using the sigmoid. For that, in this x we will substitute that summation value. If you are calculating the mathematical value, our predictor value is 0.689. So we are calculating the error value, or error value is 0.04. We try to reduce the error value. To reduce the error value, we will use the back propagation algorithm. Here we are using the back propagation gradient descent algorithm. Here I explain the back propagation algorithm very clearly. So the back propagation algorithm is otherwise called optimization algorithm, or then it is also called a convergence algorithm. See here, actually it start with some initial values and we will calculate the cost function. We can call the error function as a cost function or target function or loss function. Then we will update the values using the update function. Then we will find the minimized cost function value. This is this formula is a general formula for gradient descent algorithm that is rewritten for our based on the weight. Why we have to write the equation for weight? Actually, we will adjust the weight value and try to reduce the error value. Here we introduce one term called learning rate. It means that how fast that model will learn the data, will learn the given data. Okay, this is a gradient descent formula for a error calculation, that is weight adjustment. See, in a learning rate, if you are choosing a very small learning rate, the learning is very slow. We are missed to reach the. It will take long time to reach the convergence point. So it is a small learning rate. It will make the learning is very slow. If it is taking a very high, it's a possibility to miss a convergence point. So we have to choose a optimal learning rate. Here this is a chain rule for a, actually in the gradient descent algorithm, the term called dou error by dou w2. If you are looking to the error formula, there is no direct relationship for a error and the weight. That's why we are using the chain formula, the chain rule, dou error by dou output and dou output by dou input and dou input by dou weight. Okay. If you are calculating the derivation for that first dou, for what is the first term here? Dou error. We will calculate one by one. Dou error by dou out. Dou error by dou out. So we know the error formula as 1 by 2 target minus output square. If we will do the normal differentiation, after differentiation we'll get that output minus target. And this, we calculate that output minus target. This is the predicted output, so target is 1. So the first term we calculate that minus 0.31. Next one is second term equal to dou out by dou in. So we know that our output equal to 1 by 1 plus e power input. So we are doing the normal differentiation. After doing the differentiation, we will get the term at last output into 1 minus output. If you are substituting that value, we will get the numerical value like this. And the third term is dou input by dou weight. Actually, if you are taking which, we are going to adjust which weight value, based on that only this differentiation will happen. Here we are taking the W2. That's why this term alone present. So for this one, this numerical term is 1. We substitute all these calculated 3 numerical value in the chain rule. We will get this numerical value. So then we will substitute that value here. We are adjusting W2 because we are third term, we are differentiating with the weight W2. No, that's why we are calculating the W2. So this W is called old weight value. This W is called new weight value. This W is called old weight value. New weight value equal to old weight value minus learning rate into tau error by tau W. So the new weight to value for here is we found that 0.303. So we have to repeatedly doing this weight adjustment, different iteration up to getting the optimized weight to reduce the error value. Then we will see how to implement this implementation of RGAT using Perceptron in a Python code. So first we have to see the summary. What is the input of for Perceptron? What is the output for Perceptron? What is the formula, error formula, and how we calculate? This is a gradient descent formula. How we calculate the derivative, and after calculating derivative, that is individual derivative value, and based on these steps only we will implement the Python code. So first we will import the necessary libraries and assign some input values. These are the truth table values 0001 1011. We see the size of that input. It is 4 cross 2, that is 4 rows and 2 columns. In an array structure it look like this. Then we define the output we give us a array. That is, we know in this order 0 0 we will get the 0 0 1 1 and 0 1 0 1 and 1 1 1. For that we define the output array. For that also we define find the shape. It is in the 4 cross 1 matrix. It means that it is a 4 row and single column. Now we assign the weight to here. So the weight matrix value, we assign the weight as 0.2, 0.1, 0.2 randomly. It's a weight matrix value. After assigning, we randomly assign the bias value and the learning rate value. Then we will calculate the sigmoid function for and its derivative. So we will calculate this is a sigmoid function and we will calculate the derivative of sigmoid function. This is the main part, how many pucks we will need. Okay, so here we will feed forward input. It is a net input we are calculating. That input is given as a given to the sigmoid. Then we will calculate the error. Then we will calculating the derivative one by one. At last, we adjust the weight value. This is what we have to implement. This is a reference material I have prepared for preparing this PPT. I will refer this website. Okay, now you people understood that how clearly about the what is back propagation and how we implement the perceptron algorithm from the scratch. Okay.